Very good morning. Am I audible?
Yes, sir, audible.
Okay. So, dear esteemed keynote speaker and participants, so it is with a great pleasure and anticipation that I extend a warm welcome to our esteemed keynote speaker, Dr. Pradeep Siddham, for the second day of International Conference on Science and Humanities, Building Science, and Mechanical Engineering. And at the same time, and all to all the participants joining us today for the conference. And our keynote speaker, Dr. Pradeep Siddham, brings a wealth of knowledge and expertise in material science, specifically in the 3-night semiconductors. And we are honored to have him share his insights with us today. To all our participants, whether you are research scholars, researchers, in various fields, your presence enriches discussions and contributions to the collective learning experience of this conference. So throughout the session and discussion schedules for today, we encourage active participation, thoughtful engagement, and fruitful exchanges of ideas. Let us seize this opportunity to foster connections, explore new perspectives, and inspire each other with our shared pursuit of conference goal. So once again, a heartfelt welcome to our keynote speaker and all the participants. May our time together to enlightening, productive, and memorable. So now I request Mrs. A. Mercy, Head of the Department, Science and Humanities, to introduce the keynote speaker. Mercy, ma'am.
Yes, sir. So, good morning to everyone present here. First of all, I thank all for giving this opportunity, and also thank our management conducting this international conference on science and humanities, building construction, and mechanical engineering. So, at this moment, I am very Dr. Pradeep Sittam. He completed his degree in physics 2009, followed by PG degree in 2011 and MPhil in 2013. He attained his PhD from CEG campus, Chennai in 2018. His research work is on growth and characterization of nitrides and 3 to 5-day heterostructures by MOCVD. His research also included zinc oxide and gallium nitride heterostructures for photoelectrical chemical water splitting and low energy ion implantation on nitride and gallium nitride heterostructures. During his PhD, he was a visiting PhD fellow at Tallinn University of Technology in India. He served as a project fellow at the Inter-University Accelerator Center, New Delhi, and also he joined IIT Delhi in 2021 as a research associate before moving to Cardiff University, UK, where he worked as a research associate for 1 year on a very pilot smart applause. Due to his outstanding contribution, he was recruited by IQE Silicon, Cardiff, as a semiconductor company. He published his research more than 25 journals, and he has participated more than 10 international conferences and workshops. So now this is the right time. I hand over the session to Dr. Pradeep Siddham.
Okay. Thank you very much, Mercy, ma'am, for your introduction of the speaker. And we are delighted to have such experience leading today's session. We anticipate that the next 30 to 40 minutes will be filled with valuable insights from our speaker's presentation. Without further delay, as I said by our HOD, we are now going to pass the session to Dr. Pradeep Siddham. So over to Pradeep Siddham, sir. Dr. Pradeep Siddham.
Thank you so much, Mercy, ma'am. Actually, so Dr. Davis. Is my voice is audible for you?
Yes, your
my voice is audible?
Yeah.
Is it clear or like breaking? It's fine? Because I have to check, right? Yeah.
Initially, it was your voice is not audible, but right now it is audible. No problem. You can continue.
Like echo, any kind of things, it's all fine. Or if I want to put a mic, I can put a mic. So that's why.
No, no, no. You can start presentation.
It's very clear, sir. You can proceed.
Is my voice is audible?
Your voice is audible, but we couldn't able to see your screen.
Yeah. I will share my screen now. Sorry. Give me a second.
Yes.
Yeah. I hope it's displaying now.
Yeah. So your voice is also crystal clear, and we
Okay,
can see your
fine.
screen. Yeah.
Yeah, okay. Thank you so much, Mercy ma'am, and thank you so much, Dr. Evis. So yeah, um, good morning to all. Actually, it's 5 o'clock a.m. here, so please ignore if I have any kind of like a tired voice and all. So basically, I'm from Cardiff. So if someone, yeah, someone, if not familiar about Cardiff, so it is 300 miles in a distance of from London. So you can see here, it's a capital of Wales. So yeah, in here is a capital of Wales. It's a beautiful city. So you can see here in the map. So I'm working for IQE. IQE is a semiconductor company which mostly uh, uh, do the business on epitaxy products. So I will introduce you in the coming frames. I will introduce you what is epitaxy and what I'm working for, and it is also please believe me, like it is also very useful for you guys. Like we are in your day-to-day life everywhere, so you can see. So basically, the company is headed at IQ Europe. So and it is we also have branches around US and in Asia, Taiwan. So and I'll explain you what we are doing in the coming frames. So our founder is Drew Nelson. He founded this company in 1988, and it's still going on. Um, and the current CEO is Americo Limos. So we have all the companies obtained by IKE. So WaferTech is a substrate company. So and Galaxy Compound Semiconductors is also a silicon company. It's obtained by IKE. And EPI is in 1988. It is not actually IKE. It is called as EPI, Epitaxial Products International. So now it is set to be IKE. So coming to the outline of the session, so I'm starting with an introduction of yeah, like I will go with the introduction for a summit of like what is the compound semiconductor, where we are like experiencing these compound semiconductors in our day-to-day life. Yeah, most of you guys are maybe aware, so but still I will go from basics. So and after that, substrates, so exploring the substrates, and going for what is epi. So I was starting from the session, I was telling epitaxy, epitaxial. Oh, I will explain you what is epitaxial and how it is impacting your life every day. So epitaxial crystal growth techniques, yeah, and after that, conclusion with pros and cons of epitaxial growth, and some current researchers are going on, and products made at IKEA. Okay, coming to the session, and integrated systems, and these compound semiconductors coming in forms like this: automotives, communications, healthcare, aerospace, safety and security, IoTs, energy efficiency. Nowadays, AI and robotics are all developing now. So already AI is already impacted your life already. So okay, and okay, so we can see, like I have described this compound semiconductor is coming in this form. So let's see in our day-to-day life how this compound semiconductor is there. Okay, for example, if you see here, you have a lot of charges here, like so you will have like a different charger for laptop, different charger for mobile phone, and different chargers for your gadgets. Okay, so if we make these all chargers into a single charger, that will single charger that will give you all the uses. Like you can charge a computer or a laptop or or your gadgets, mobile phone, everything. So how can be it is it is achieved? How it is achieved? So you can see, so it cannot be done by a single silicon elemental semiconductor. Is because of a development of compound semiconductor only it happened. So uh, gallium nitride is already in your life. So you can see the nowadays fast chargers are coming from uh, gallium nitride power controllers. You can see if you open the uh, this high fast charger, yeah. So this is a power controller. So you can see this power controller is packaged now, and it have a gallium nitride inside. But where this gallium nitride came from, the chips. You can see here the gallium nitride hemp, high electron mobility transistors, and a silicon MOSFET for control. So you can see here, if you open this chip, uh, or this modulator, you can see here. So the if you see this the overall description, you can see here the gallium nitride and silicon combinedly have the transistors here. Especially GaN works for the high electron mobility transistor, and silicon for MOSFET. So if you go into detail, so these GaN have this epitaxial structure here with a substrate of silicon. Both are integrated, and if you see if you wonder where this gallium nitride the epitaxial layers came from, it came from a small wafer 1 into 1 centimeter. So from if you wonder where this 1 into 1 wafer came from, it's like it is came from a substrate or a silicon substrate deposited with gallium nitride. So you can see I will try to explain you these layers. What are all these layers? First of all, going to these layers, we have to understand where this silicon substrate are come from. So if you check these are the combination of elemental semiconductor and the compound semiconductor. So before going to the substrates and all, so we can check the basics of we can refresh our basics of our semiconductor. So semiconductor is divided into uh, two parts. It's simple and compound. So simple or elemental is said to be silicon and germanium. And compound, you can see 3,5, 2,4, and 4,4. So you can see a 3,5 or gallium arsenide, indium phosphide, and gallium nitride, and more combinations you can see here. Aluminum arsenide or gallium arsenide. So yeah, indium nitride, gallium nitride. So you can see a lot of combinations here: 2, 3, 4, 5, 6. Now I'm going to concentrate only on the compound semiconductors. So we can start with the first, yeah, how it is described as first gen, second gen, and third gen. So we are going with the band gap actually. So if we start the first generation semiconductor having a less band gap, so which is around so having the energy and the wavelength around the IR region. So in the field of semiconductor, the first generation semiconductor is silicon, the second generation semiconductor is gallium arsenide, and third gen is silicon carbide and gallium nitride. So how these generations are separated, like first and second generation semiconductor have low energy, as I said, low energy gap materials with values of 1.12 electron volt and 1.43 electron volt respectively. The energy gaps of third generation are very high. So you can see 3.2 electron volt to 3.4 electron volt, which is around the ultraviolet region. So the so what are the applications of third gen encountering? So is they are overcoming the first gen and second gen's uh, drawbacks, like high temperature. They can withstand high temperature, high voltage, and high current compared with first and second generation. So now I can go in more like day-to-day applications, like how this frequency and power of this gallium nitride and silicon carbide is separated. So you can see I have already told you, like silicon carbide and gallium nitride comes in under the for third gen. So you can see the day-to-day applications here, how these silicon carbide and the gallium nitride are impacting your life. So you can see here, the gallium nitride is already occupied your life with a uh, uh, computer or adapter or power devices. You can see here, and and very high power applications are covered by silicon carbide. You can see central PVs, EVs, and some robotics. You can see here GaN has a faster frequency suitable for consumer device charging, light gasoline power, hybrid power, and 5G ratio frequencies. So you can see here silicon carbide covers the higher voltages such as electric vehicles and supercharging stations, vehicles, and energy sources. So how these silicon carbide and gallium nitride looks like? So yeah, I have already showed you how these chips are existing in your day-to-day life applications. So but initial phase, if you see them, so it will be like this only as a chips, IC chips. So how these are like divided in the applications is, so silicon carbide related to us, uh, interrelated to the applications. So I'll show you in the next frame. If you see, so if you see the wavelengths, if you see in the wavelengths, so you can see a blue LED. So blue LED is impacting in your life because whatever the white lights you are looking at in our day-to-day lives are all coming from these LEDs. And these blue LEDs are covered with a white phosphor. Then we will get a we are getting a white light there. So but a full-fledged pure compound semiconductor white light is still developing stage, is in still developing stage. So you can see the UV LEDs here, or UV